Welcome to the abstract of multidimensional RF pulse design with known spatial encoding imperfections. Multidimensional RF pulses have many uses including localization, motion tracking, and inner-volume imaging. Excitation performance can often be compromised by hardware limitations and experimental distortions, for example, limited peak RF power, star limit, and gradient imperfections. In recent years, these issues have been addressed. One notable example is the reverse method with dynamic field correction published by Cavusciolo et al. In 2017. However, concomitant fields, also known as Maxwell fields, haven't been considered during the pulse designs. These exist whenever the linear gradients are active and are increasingly important at low field strengths with higher gradient performance. Based on Bernstein et al., the concomitant fields can be described. It is possible to consider the concomitant fields in the reverse design. However, transforming them into the rotating frame requires fine sampling intervals on the order of nanoseconds. So directly solving the least square problem using the reverse design seems impractical, and for this reason we introduce a new approximation. In this study, we demonstrate a new multidimensional RF pulse design that incorporates the concomitant field effects. We estimate the concomitant field similar as the Bloch-Siegert approximation. Starting from the reference frame, we have B0 and gradient field terms on the longitudinal and concomitant field BC on the transverse plane. They together form the purple magnetic field vector written as below. To perform the approximation, we extract this plane. Under assumption that the length of B0 is greatly larger than BC, the approximated BC tilde is the amount that the purple vector exceeds the orange vector. Therefore, the purple magnetic field can also be written as the BC tilde plus the mean field and gradient field terms. Deriving from this equation, the BC tilde can be treated as the combination of higher order gradient terms. In the rotating frame, the overall B effective can be expressed as the vector sum of the B1 gradient field terms and of resonance with extra BC tilde. Therefore, we can use this formula in the Bloch simulations substituted with the derived BC tilde. We evaluated the estimation accuracy across field strengths using the 2D RF pulse. Here are excitation patterns. Using the reference method with the concomitant field considered, we observed that at higher field strengths, the patterns are almost the same as the original. At low fields, the errors become obvious. With our proposed method, they are almost identical to the reference at higher fields and has slightly differences in the phase at low fields. Quantitatively, we confirm that the estimation error can be less than 5% when above 0.2 Tesla, and is smaller for larger B0. Next, we evaluate the performance of multidimensional RF pulse using the reverse and proposed methods. We show that the imaginary and real parts of the designed excitation, three circumstances are considered. For B0 dependence, from 0.55 Tesla to 7 Tesla using the reverse method, we see that the errors are large at low fields and become less with higher field strengths. Whereas the proposed method, we observe the results of all cases are more uniform with reduced errors. This improvement is greatest at lower fields. Similarly, for the off-isocenter dependence at 0.55 Tesla using the reverse method, the concomitant field effects increase with displacement. But the proposed method shows less errors in all cases, with the greatest improvement away from the isocenter. Further, we examined the impact of pulse durations. The concomitant field-induced errors increased from 16 to 51 milliseconds. However, we see better profiles for the proposed method in all cases, and it is more obvious with longer pulse. With that, we demonstrate a new multidimensional RF pulse design that incorporates the concomitant field effects. This provides more accurate excitations, and the impact is greatest in scenarios where the concomitant field effects are substantial. And this is a simulation study. Our experimental verification is forthcoming, and our group are particularly interested in the exploring potential applications using multidimensional RF pulses at low field strengths with high performance gradient systems. Thanks for listening.